Good morning, guys. Happy Tuesday. Today we're going to be covering 3.1. Your quiz is today. I know that yesterday it had you try the 3.1 checkup. Oh, so your quiz is tomorrow. Sorry about that. So hopefully today will help cover anything that you weren't quite understanding. And I also shared some Unit 3 notes with you. Can you give me a green check mark if you were able to save those notes to your desktop? Did these Unit 3 notes come through? Dakota and Stefan, can you let me know in the chat area? Okay, excellent, fabulous. Okay, thanks for the reminder about the answer key for the checkup. I will definitely post that. Let me make a quick little note. Okay, great. So in these notes, I created these notes last night. What it has in there are some notes about inverses and also all of the domains and ranges for the inverse functions. So I would definitely print those out, keep them handy, that way you don't have to memorize them. I'm going to go over it with you today to make sure that you do understand how I got those, but the nice little chart, that way you have them handy in your notes. You won't have to go look them up moving forward. So today's essential question, I will put this back up again at the end, for week 8 is how many coterminal angles does a cosine or sine function, cosine or sine trig relation have? We're going to talk later today about the difference between a relation and a function. So this particular question is asking you about how many coterminal angles a relation has. And then secondly, how do you find those solutions? Since I use the word solutions, I'm sort of giving you a hint that there's going to be more than one coterminal angle. So again, hi Nicole. I'm going to put this question up again at the very end of the session. I just wanted you guys to know where we were headed today for our live session. So we're going to be talking about coterminal angles of relations and how to find all of those solutions. So trig inverses. Here's why we use trig inverses. We use trig inverses when I want to find an angle. If I say sine theta equals 1/2, the way that I would find that angle is to do an inverse. Think back in math for a second to Algebra 1. Let me put up a quick problem. If I have 2 times x equals 10, we all know that we do the opposite to get rid of it. We divide by 2. Well, in this case right here, this says sine times theta. But I'm not just allowed to divide by sine. I can't do that because the sine and the unknown, they are attached together. So what we learned in geometry and first semester pre-calc is that in order to solve this, I would have to do the inverse of sine. So this is why we use inverses. We use inverses to find missing angles. So here's kind of the question that we're going to ask ourselves today. What values of x make these statements true? And what we're going to notice is sometimes they're going to use the theta symbol, and sometimes they're going to replace it with a variable like x. Here's how we're going to look at it. We're going to look at this from 2 perspectives. We're first going to look at it on the unit circle, and then secondly, we're going to graph sine x and see what the graph looks like as well. So let's all go to the unit circle, and we're going to find out where sine x equals 1/2. So here's my unit circle. Sine represents your y value. Everybody agree with that? So if I'm looking for sine x equals 1/2, we learned last unit, or unit 1, when we were learning about the unit circle, that sine is opposite over hypotenuse, and your opposite is your y value. Hypotenuse is always a 1 on a unit circle, so that's why all we care about is the y value. So let's look on my unit circle and find some places where my y is a 1/2. Here my y is a 1/2. Is there anywhere else where my y is a 1/2? There certainly is. Right over here my y is a 1/2. So I actually have 2 possible solutions for x where my y value is a 1/2. Those angles are pi over 6, right here, and 5 pi over 6. Is everybody okay with how I found those 2 angles? I was looking for the spots where my y value was a 1/2, here and here. Okay, great. Thanks for the green check marks, and I'll clear you back out there. But here's the deal. Are these going to be my only two angles where my y value is going to be a 1/2? The answer is no. Those are not my only two answers. Let's talk about this. What if I were to start from this point and I were to go all the way around the circle again? Then I would be back at that same spot again, and then my y would be 1/2. Do you guys remember, how do you get all the way around the circle? What would I be adding to my problem to go all the way around the circle to this point again? Okay, you're right, it is 360 degrees, but let's talk in terms of pi. So since I'm saying that this is pi over 6, how much would I be adding to go all the way, one whole rotation around my circle? Good job, Stefan got it. It's 2 pi. What if I went all the way around my circle again? Then I end up back at the same point. How did I get there? I added another 2 pi. So what we're going to learn is that there are tons and tons and tons of solutions. These are called coterminal angles. You should have read about that in your 3.1 lesson. So coterminal angles are all of your possible solutions for our problem. So remember, my original problem was, where does sine of x equal 1/2? There are many, many, many answers. So let's talk about how we're going to write all of these crazy answers in just a minute. But first, let's graph sine of x. So here's the graph of sine of x. So first I told you we're going to look at the answer two ways. First we looked at it on the unit circle. Now we're going to look at it on the graph. So if I draw where y is 1/2, that would be right here. So now if I find all of the points where y is 1/2, I'm going to have quite a few solutions. Is everybody okay with what I'm doing so far? Can you give me a green check mark? Based on my graph, I'm just picking out all the spots where it has a 1/2 for my y. Okay, excellent. But again, how am I going to write all of these possible answers? Well, there's a formula that we're going to use. So these are the ones that we got from the unit circle. We had pi over 6. We're going to have 5 pi over 6. And there's going to be a pattern to these answers. So what's the pattern? The pattern is you're going to take your original reference angle and you're going to plus or minus 2 pi. They put the n at the end because that stands for number of rotations. So for instance, let's talk about our first, pi over 6. Let's say plus 2 pi. The next time I was going to say pi over 6 plus 2 pi, because my first time I just did 1 rotation. The second time I could do 2 rotations. The third time I could do 3 rotations, and it just keeps going and going and going, right? And these could be pluses or minuses. So that's why instead of writing in 1 rotation, 2 rotations, 3 rotations, we're just going to use the letter n. So I did have 2 reference angles. So my first reference angle that we found from my original unit circle was pi over 6 plus or minus 2 pi n. What was our other reference angle from the original unit circle? Do you guys remember? What was the other spot on our unit circle where it also equaled 1/2? Good job. 5 pi over 6 was our other one. So we're going to say 5 pi over 6 plus or minus 2 pi n. So I have 2 choices. And by writing it this way, this gives me all of my coterminal angles. So let me give you a quick minute to jot down any notes that you would like to do before we move on to the next slide. But this one in the box at the top, this is our formula for finding all of the coterminal angles. Hint, hint, that's part of your essential question for the day. Let me clear out your check marks. Can you guys give me a check mark if you understand what I mean by reference angles? And if you don't, we can go back to the first unit circle slide. They are the points on your original unit circle where you get that solution. And usually there's more than one right answer. We're going to try it again with cosine, and hopefully that will make more sense. Okay, so on our picture, there is a pattern to all of these spots where it's going to cross at 1/2. And what we just said below was that here's how you write all of the coterminal angles. So pi over 6, and then plus or minus 2 pi n, then 5 pi over 6 plus 2 pi n. The way that I find these original ones is I go back to my unit circle. So now let's try, and I'm going to lock the room at this point. I just wanted you guys to know why I put that on the screen. Once we are so many minutes into the session, I don't want people popping in because you've missed too much at that point. So just be sure that you are here on time. Does that make sense? Because there's no point in getting half of it, right? You might as well just watch the recording at that point. Okay, great. Okay, next. So how would it be different if I asked about cosine? So this time if my equation is cosine x equals 1/2, I want all the points on my unit circle where my cosine is a 1/2. Well, we learned in Unit 1 that cosine are simply your x values. Right? The one that we did earlier was sine, and our sine are our y values. So this time I'm looking for where are my x values 1/2. So let's look on our unit circle and highlight those spots where my x value is 1/2. So I have one right there at pi over 3. And this time I do have another solution, but this time I have to go all the way around my unit circle to find it. Down here, I also have a positive 1/2 for my x, 5 pi over 3. So let's try and write our solution set together. They call them solution sets since it is more than one correct answer. So my two reference angles this time, I have a pi over 3 and I have a 5 pi over 3. So to write all of my possible terminal angles to these, I'm going to add a plus or minus 2 pi n plus or minus 2 pi n. And again, the reason that it's plus or minus is because if I start at pi over 3 and I go one whole rotation, that's adding 2 pi to it. If I go to pi over 3 and I subtract 2 pi, that's going in this direction, and I get right back there. Just to make sure everybody's super clear on how they got some of their other values, let's actually try adding plus 2 pi to one of our answers just to see. So let's take our pi over 3, and let's try adding 2 pi to it. Well, how do I add these two when they don't have like bases? I need to make them have like bases. So what if I made, instead of 2 pi, I can say 6 pi over 3. Is everybody okay with me doing that? 2 pi is the same as 6 divided by 3. I'm just making them so that they have common bases. So now I can actually add them together. So 1 pi over 3 plus 6 pi over 3 would give me 7 pi over 3. So you might have been wondering, how did they get all those extra fractions in there for those coterminal angles? They're just adding or subtracting 2 pi to them. Can I get a smiley face if that made sense? This is how you'll write your answer up here, just with the plus or minus 2 pi n. But again, I just wanted you guys to make sure you knew how they got some of those other funky numbers in there. They just actually added or subtracted 2 pi to them. Okay. What's really cool this unit is that there is a special way we can tell that it's an inverse, and we did learn this in Algebra 2 as well. When you guys see a -1 up there, that's going to denote that it's an inverse. It's not an exponent. Okay, so you're not saying sine squared. That's not what it means anymore. Now that we're in pre-calculus, when we see a superscripted number, we think of it like an exponent because it's raised. But when it's a -1, that's going to denote that it's an inverse. That's just an important note to make. The other way that they could say inverse is they can say, instead of sine to the -1, they can say arc sine, arc cosine, arc tangent, arc cosecant. You guys get the idea. So there's two ways to denote that it's an inverse. Either it's going to be to the -1 power, or you're going to say arc sine. And what does it mean to take the inverse of a number? It means that we're looking for the coordinate at that point. So just like we did here, going back a little bit, when I said sine x to the equals 1/2, what I was really saying is sine to the -1 of 1/2. I want to know at what points on the graph are my values, is my angle a 1/2. So this is just another way of saying it. Or I could have said arc sine of the 1/2. These are all just the same way of writing, well, different ways of writing the same thing. So 2 new ways to write inverse. And they're actually not new because we did do this way before. The only one that's new is this arc cosine, adding arc. So what they got into at the end of 3.1 was going over the difference between a function and a relation. This we also learned previously, but I know it's been a while since we've done some of these things. So let's re-go over them. In order for something to be a function, it has to pass the vertical line test. So we remember that, you know, here's my graph, here's my straight line. When you take your straight line and you go all the way across it, it only hits your graph one time in every single place. This would pass the vertical line test. If I were to do the inverse of this, the inverse flips it, turns it, whatever else, like this. Now when I take my vertical line test, oh, it hits 2 times. You guys see that? It hits 2 times. So the inverse is not a function. They're going to teach us how to ensure that our inverses are also functions. In order to ensure that when I take something and I flip it, the inverse, that it's also a function, we do what's called restricting the domain. So we're going to practice, how do I do that today? How do I restrict the domain? So just a quick reminder about what an inverse actually is. It's where you swap your x and your y value in your equation. So let's do a basic one real fast. If I had y equals 2x, the inverse of that would be x equals 2y. So I'd divide by 2, and I would get y equals 1/2 x. They are inverses of each other. And when you graph them, when you graph the original and you graph the inverse, they're just flipped. It's a flipped version. It's where your x's become your y's and your y's became your x's. So let's take a peek at our sine graph right here. Here's our parent function for our sine graph. It crosses through 0, 0. We knew that. Pi halves is 1. At pi it's 0. It's just this nice sinusoidal curve. When we do the inverse of it, and by the way, is sine x a function? Does it pass the vertical line test? What do you guys think? Is sine x a function? You guys are absolutely right. Yeah, oops, yes, sine x is a function. Yes. When I flip all of my x and y values, I get this crazy graph over here. Is the inverse a function? So the inverse of sine x, is it a function? No, it's not a function right now, but I'm going to teach you how to make it a function. Before we move on to the next slide, I want us to talk about domain and range of these original graphs. So domain are your x values. So everybody look at the original graph. As far as x's go, it's going all the way left, it's going all the way right. So my domain of my original would be -infinity to +infinity. That would be my domain. Everybody good with that? We did this last unit. What would my range be? Range are my y values. Where does this graph go on your range as far as up and down goes? It's a very restricted area. Can you type that in for me? What is the range of your original sine x function? What are your up and down values? Perfect. And I like how some of you guys wrote them with these braces in there, those brackets in there. So -1 to 1. Remember, when you have the squared looking one, it includes that value because at pi halves it is 1, right? It's not less than 1, it actually equals 1. So when this number is included, you have to use this symbol. When the number is not included, you use the parenthesis. Everybody okay with that idea? Because you can't include the negative infinity because that's not, you can't ever really reach that value, so that's why that one is always a parenthesis. Over here on the right, let's do domain and range for the inverse. So my domain, what's your x value on the inverse? You might be seeing a pattern here. What's your x values? What's your side-to-side values? From where to where? -1 to 1, including both of those numbers. What's your range on the inverse? What's the range? What's the up? What's the down? Good job. You guys are right. Negative infinity to positive infinity. Does anybody see a pattern here? Look at your original. Look at your inverse. Do we see a pattern? Yes. They have swapped places. Hey, wait a minute. That's what an inverse means, right? Your x's and your y's swap. What's domain? Your x. What's range? Your y. So when we do the inverse, they have switched places. So that only makes sense that that's what's going to happen when we take the inverse. So with that in mind, let's try this. This is a very small portion of our sine graph from the last page. Now why did they pick this specific portion? Because when I take the inverse, it is still going to be a function. Notice that this is just a little section of your original. And it's actually the perfect section that when you take the inverse, it is also still a function. They both now pass the vertical line test. If I were to include more of this function, oops, I need a different color. If I were to have included more of this function, when I flip it, it would not have been a function. So I have to just pick the portions that are going to help it to be a function when I take the inverse. There's a name for the part of the graph that you pick, and we'll be going over that in just a minute. But let's go ahead and let's take a peek at what restrictions were placed on domain and range. So let's look at our original over here on the left, and let's do our domain and range. So my domain, what's my x? What's my side to side? These are kind of hard to type in, so I'll do them with you. They went from -π/2 to +π/2. What's your range? What's your up and down? It is still -1 to 1. Can I get a smiley face if you're with me on this? If you understood what I put for domain and range according to this picture? Here's what's also really cool. Remember how one whole period was 2π? Guess what restrictions we put on it to make it a function? We made it just a pi. We did half, right? We took 2π, which is a whole period, and we're just showing half of that. We're showing half of the graph. Half of one period makes it a function. Kind of cool. So what would my inverse be? What would my inverse domain and range be? Well, we just talked about it. They just swap places. So my domain would be -1 to 1, and my range would be -π/2 to π/2. So they just swap places. Sometimes they're also going to write it like this too, just so you get used to it. They could say -π/2 is in between x, is in between π/2. So -π/2 is less than or equal to x is less than or equal to π/2. So I'm just showing you, they might write it either way. These are the same thing. Okay, so are we okay with what restrictions they placed on there? We just take a peek at their graph. This piece of the graph has a special name. Does anybody remember the name of this piece from the 3.1 tutorial online? This piece of the graph has a special name. It is called the principal branch. The principal branch is the widely accepted portion of the graph that makes it a function. It means they're not going to make you pick a piece of the function. They've already picked it for you. The principal branch is the main portion of the graph that makes it a function when you take the inverse. Everybody okay with that word? So we don't have to guess about the principal branch. It's already been determined for us. It's what makes it a function. So in your book, there is a huge difference, not book, all my lesson. There's a big difference between when I use a lowercase s and when I use a big capital S. Lowercase c, capital C. Here's the main difference. When it's a lowercase, that's a function. Oh, sorry. Just kidding. I just told you backwards. When they use a lowercase, that is a relation. When they use a capital, that's a function. Lowercase, relation, capital, function. Functions are really important to us, again, because we know that that means they pass the vertical line test. That's going to be when they're using those principal branches. So when you see a summary like this, and it gives it to you like this in the book, what they're wanting here, remember that very first problem we did today with the sign of 1/2, and I wanted to know where does your value equal 1/2, and there were lots and lots of answers? That was a relation because it had coterminal angles. It had tons and tons of answers. If I give it to you as a capital, that's not going to have tons and tons of answers. I'm only looking for it in a specific section of your graph. Not the whole graph round and round and round that circle, just a very specific section of the graph. Does that make sense, the difference between the two? So relations have tons and tons of terminal angles. When it's telling you it's a function, it's talking about a very specific portion of your graph, just like we saw with that principal branch. So how are you going to know what all of these domains and ranges are? At the beginning of the session today, I shared those notes with you. I want you to print them out. Here's part of what is on those notes. It's a domain and range chart, and this is what I file transferred to you. And what it's showing you is for these functions, notice it's calling them a function. Notice they're all capitalized. The capitalization also tells us it's a function. They are telling you the domain and range for the principal branches. They are saying, here's the domain, here's the range. Domain, range. So you don't have to pick out that section of the graph. This is telling you what the section of the graph is. Can I get a smiley face if that makes sense? Or please ask a question if it doesn't. So you would graph sine x if you're thinking, well, how do I know what that looks like? We all know what a regular sine x looks like, and then you're only looking at the portion of the graph on the domain value from -1 to 1. Does that make sense? You're going to graph cosine x, you're only looking at the domain from -1 to 1. And remember, these are inverses. These are inverses. So if you want to know what the original looks like, you would just swap your domain and range. That's why this is -pi-halves to pi-halves. So just remember you can flip-flop these two, going between inverse and regular function. Inverse and regular function, they can swap places. So print that out, keep that handy. I also put a couple other notes to you at the top of the page about principal branches and inverses. So print those out, keep them handy. So here's our essential question again. This was pretty much answered in the first couple slides today. It's how many coterminal angles does a cosine or sine trig relation have? So notice I didn't say function, I said relation. And how do we find these solutions? This last question just might be a formula that we did on the first couple slides. Okay, so that takes care of 3.1, which is your quiz for tomorrow. I'm going to go in right now and upload your 3.1 answer key. The rest of the week, Thursday, Friday, you're working on 3.2. And so next session, on next Tuesday, we're going to be doing 3.2 and 3.3 together. I like for you guys to come prepared and already have tried the material on your own, and then I just go over the parts that I feel need clarification. So I hope that this was helpful, and I hope you guys all have a great day. And for Nicole and Josh, were you guys able to download the Unit 3 notes that came through, that popped through? And Dakota, I'll get back to your question in just a second. Okay, I'll go ahead and stop the recording.